Architects often specify rammed earth for its passive sustainability. When those same designs are run through standard simulation software, they consistently fail predictive energy standards. The error originates in how the industry models the data. Standard energy software evaluates a rammed earth wall using the exact same parameters it uses for conventional concrete or steel. These simulation engines require rigid, unchanging thermodynamic inputs to calculate a building's performance over time. But rammed earth is a high-growth thermal system. This means its thermal resistance and structural properties constantly fluctuate depending on the ambient moisture in the air. By treating the material as static and dead, standard models miss its passive climate regulation capabilities, causing engineers to consistently overestimate the required size of HVAC systems. To make rammed earth code compliant, the building industry must transition away from qualitative historical wisdom. We have to rely on rigorous, measurable material science based on recent peer-reviewed data. Understanding this dynamic coupling of moisture and temperature is the only way to accurately size mechanical systems and utilize the material's actual performance metrics. A recent study published in China's Sustainability Journal finally quantified the precise high-growth thermal relationship in earthen walls. This graph shows how sensitive the material is. As moisture increases to 14%, thermal conductivity rises sharply from 0.77 to 1.38, a 79% increase. When dynamic variables are engaged in simulation, predicted heating loads in cold climates drop by 15 to 17%. Historically, structural engineers have had to cobble together incomplete thermal and vapor data, pulling absorption rates from one soil test and permeability from another, usually under completely different conditions. A French collaborative study solved this baseline problem by running uniform material testing on a single, well-documented source, the 2019 La Orangerie building in Lyon. 4 different laboratories characterized everything from vapor permeability to moisture absorption on the exact same soil, exposing extreme physical sensitivities. They found that a mere 4% difference in the density of the packed earth altered its thermal conductivity by 17%. They also observed that while grain size barely affects moisture absorption, high ambient humidity nearly doubles the material's hysteresis, which is the delay in how the wall absorbs and releases water compared to the surrounding air. Because they mapped these behaviors linearly across different compositions, the researchers developed approximation coefficients. Engineers can now model accurate thermal conductivity without paying for site-specific soil lab testing on every project. Beyond thermal dynamics, earthen architecture faces a severe structural barrier. Plain rammed earth averages a compressive strength of around 4.0 megapascals, or MPa, which falls short of many modern load-bearing building codes. To solve this, researchers in Egypt tested various stabilization composites, searching for an optimized high-strength mixture. The optimal mixture they identified is designated CDW30C2. The recipe is specific: 30% recycled construction demolition rubble, 2% lime, and the remainder local soil. This mixture achieves strength through 2 mechanisms. First, the angular, jagged particles of crushed concrete waste physically interlock under pressure. Second, calcium oxide in the lime triggers a pozzolanic reaction, forming binding cement-like crystals within the microscopic gaps. At 28 days of curing, this composite hits 9.3 megapascals, more than doubling the baseline strength of plain rammed earth. The mixture maintains a highly efficient thermal conductivity of 0.88 watts per meter Kelvin, all while redirecting commercial construction waste away from landfills. This exact ratio works because it represents the mathematical balance point where the physical interlocking of the rubble and the chemical binding of the lime optimize without interfering with each other. Initial compressive strength is only one variable in a building's life cycle. Long-term service life requires engineering for weathering and environmental degradation. To understand extreme longevity, an MIT team analyzed dry material piles preserved at a Pompeian construction site from 79 CE, investigating how ancient Roman structures have outlasted modern concrete. Their chemical analysis revealed a process called hot mixing. Contrary to ancient texts, the Romans ground quicklime dry, mixed it with volcanic ash, and added water strictly as the final step. This high-heat reaction trapped brittle lime clasts directly within the concrete matrix. When structural microcracks form, These trapped clasts dissolve upon contact with ambient moisture. The resulting calcium-rich fluid quickly recrystallizes, actively healing the crack. Similar chemical diagnostics are now validating the extreme longevity of traditional Chinese earthen architecture, like this 160-year-old rammed earth structure in Fujian. When researchers assessed the building prior to a relocation project, they found severe microcracking, porosity, and mineral loss isolated on the unprotected east-facing walls. The preserved walls featured a traditional soot and lime coating known as Wu Yanhui. Modern builders have historically dismissed this treatment as purely aesthetic. This Raman spectroscopy chart plots scattered laser light to identify exact molecular structures. Looking at the intact interior walls, researchers found sharp vertical spikes at 1350 and 1580 inverse centimeters, proving the soot coating maintains an active, protective carbon presence. The coating functions as a sacrificial layer. It degrades preferentially, absorbing moisture fluctuations and environmental stress to protect the structural load-bearing wall beneath it. These ancient quicklime inclusions and traditional surface treatments function on the exact same principle. They are active, renewable chemical buffers that practitioners can integrate directly into modern conservation and construction protocols. The research surrounding earthen architecture has matured. Vague assertions about sustainability have been replaced by rigorous, reproducible mechanism documentation. We now have the data to accurately size HVAC systems using dynamic hygrothermal modeling, hit modern code-compliant compressive strength using demolition laced, and ensure longevity using diagnostically proven sacrificial coatings. The primary takeaway from this data is that rammed earth is not a static monolithic material. It is a highly tunable construction matrix. Its final performance characteristics are dictated entirely by how engineers manipulate variables in moisture content, compaction energy, and stabilization chemistry. Mastering those specific variables and utilizing these proven approximation coefficients is how the industry elevates earthen architecture into mainstream structural engineering.